So I'm going to work problems number 25 and 67 for Chapter 4. Take a second, pause, and read this question. The first thing you need to do is draw free body diagrams for the two buckets. I'm going to call that one bucket number 1 and bucket number 2. And I'm going to draw my free body diagrams for buckets number 1 and bucket number 2. Now, bucket number 1 is being supported by some tensional force up here. I'm going to call that force of tension on bucket 1. It's going to be that guy right there. It's going to have always its weight, mass of bucket 1 multiplied by gravity. And lastly, it's going to have some force of tension from bucket number 2. I'm going to draw that guy right there, force tension number 2. Now bucket number 2 is going to have its mass times gravity in the downwards direction, and then it's going to have the force of tension number 2 supporting it. So mass of bucket number 2 multiplied by the gravity, and this is the force of tension number 2. A couple of things to note for this system is these two are an action-reaction pair, so they are equal magnitude, opposite directions. If you solve for f sub 2 in one of these diagrams, you can apply it to the other one. And then the other thing to recognize is this is a system that is held together by tension, so the acceleration of bucket number 1 must be equal to the acceleration of bucket number 2, must be equal to the acceleration of the system. If you remember that box problem I did where the boxes were sliding across the floor, the same type of thing applies here. You solve for the acceleration of the system, you can apply that to 1 and number 2. So it says if the buckets are at rest, what is the tension in each cord? So the first thing that we can do is let's take a look at bucket number 2. It looks simpler. And if I write Newton's second law, some of the forces in the y direction for bucket number 2, that's going to be equal to the, that's going to be equal to the mass of 2 multiplied by the acceleration of 2. It says if the buckets are at rest, therefore they are not accelerating, so the acceleration is equal to 0. Now I can write the forces as force of tension number 2 in the upwards direction minus mass 2 times gravity. So if I add mass times gravity to both sides, I can say that the force of tension number 2 must be equal to the mass times gravity. Now I know what the mass is, I know what the gravity is, so the force of tension number 2 must be equal to 3.2 kilograms multiplied by 9.8 meters per second squared, must be equal to 31 newtons. Now for bucket number 1, if I write the same thing, the sum of the forces in the y direction on bucket number 1 also is not accelerating. Mass times acceleration must be equal to 0. I'm going to have force of tension number 1 in the upwards direction. I'm going to have the force of tension number 2 downwards, and the mass times gravity also in the downwards direction. Now I'm solving for force of tension number 1, so I'm going to add those two to both sides, and I'm going to write force of tension number 1 is equal to the force of tension number 2 plus the mass 1 multiplied by gravity. I know what force of tension number 2 is, I know what the mass is, so force of tension number 1 is going to be equal to 31 newtons plus the mass is going to be 3.2 kilograms, and the gravity is going to be 9.8 meters per second squared. So force of tension number 2 is going to be our force of tension number 1 is going to be 63 newtons. Now, to solve the second part of this problem, if the two buckets are pulled upwards with an acceleration of 1.25 meters per second squared by the upper cord, calculate the tension in each cord. Now this is actually going to be fairly similar. I mean, the free body diagrams all stay the same. Now I have some acceleration in the system, so unlike before where I had no acceleration and I set this guy right here equal to 0, now all I'm going to do is set it equal to its mass multiplied by its acceleration, and I can go ahead and use the same setup right here. So now that I've wiped this guy a little bit out here, now I'm going to say the sum of the forces in the y direction is going to be the mass 2 multiplied by the acceleration, and that's going to be still the same, only now I have an acceleration. So all I got to do is solve this same problem for force of tension number 2. Say force of tension number 2 is going to be equal to the mass sub 2 times the acceleration plus the mass of 2 times gravity. So I'm just going to rewrite that, m2 multiplied by the acceleration plus mass sub 2 multiplied by gravity. So that's going to be 3.2 multiplied by 1.25 meters per second squared. That is the acceleration defined right here, plus 3.2 multiplied by gravity, 9.8. So the force of tension number 2 is going to come out to be about 35 newtons. Same thing with the initial bucket. Sum of forces in the y direction is going to be the mass times 1 multiplied by the acceleration of the system, and I have the same forces right here. Now all I do is I rewrite everything. I put force tension number 1 on one side, so I add this and I add this to both sides, and I say force of tension number 1 is going to be mass 1 multiplied by the acceleration plus the force of tension number 2 plus mass times gravity. I go ahead and I plug all this stuff in. 3.2 multiplied by the acceleration of the system, 1.25 meters per second squared, plus 35 newtons, plus 3.2 multiplied by gravity, 9.8. And at the end of the day, I come up with 71 newtons to be the force of tension number 1. Okay, so for 67 I'm going to work an incline problem with a pulley. You're going to see several of these in your lecture problems. Now the one thing about the pulley is all it does is redirect the tension. So we know that here we're going to have some tensional force. All the pulley does is it redirects the direction of it such that here we have the same tensional force. If you really wanted to, get nitty-gritty, there's going to be 2 other tensional forces there and there, but for your intents and purposes, all it does is redirect the tensional force. These are still an action-reaction pair, in a way, close enough, and these 2 tensional forces are going to be the same. If we had a pulley supporting 2 boxes, like what's called an Atwood machine, the same type of thing is going to occur. There's going to be some tensional force right there that's going to end up being equal to the force of tension right there. Pulley merely redirects it. Also in this system, there are these 2 masses are connected by the string, so the acceleration is going to be the same for both mass A and mass B. So let me jump right to it and start drawing my free body diagrams. First, for mass number B, that is going to have some tensional force in the upwards direction, and it's going to have its weight in the downwards direction, mass of B multiplied by gravity. Now, for mass number A, it's a little bit more difficult. It's on an incline, but we're already kind of familiar with inclines, right? You've worked those problems in the book, or the examples in the book. So here I have mass number A, and it's going to have several forces on it. The normal force is always perpendicular to the surface. Normal force. It's going to have, of course, its weight in the downwards direction, mass of A multiplied by gravity. It's being dragged in the upwards direction by the same tensional force, force of tension. Mention real quick here that it says as mass of B moves down, that says that the motion for this guy is going to be that way, and the motion for block number A is going to be up the ramp. And because of that, we're going to have some frictional force that's going to oppose the motion. And what I want to do is I want to do the same thing where I define my coordinate system to have y in that direction and x in that direction. You can see that the normal force is in the positive y direction, the friction and tensional forces are in the plus and minus x directions. So all I need to do is I need to break my weight force up into its two components, the weight in the y direction, the weight in the x direction. So I'm going to write those really quickly. The force of the weight in the y direction is going to be the mass of A multiplied by gravity. We know that that angle must be equal to that angle, so that's going to be the mass of A times gravity times the cosine of that angle. The force of the weight in the x direction is going to be equal to the mass times gravity times the sine of that angle right there. So that's going to be those two components, force of the weight in the x, force of the weight in the y. And I've broken that guy up into its two components. Now let me write Newton's second law for the two systems right here. I'm going to say, first of all, I have no forces for mass number B in the x direction. I'm not even going to waste my ink writing that out. I'm going to first write out, though, some of the forces in the y direction for mass B. So, scoot this guy over just a hair. Some of the forces in the y direction for mass number B, I have the tensional force upwards and the mass times gravity downwards. So force of tension minus mass of B multiplied by gravity. That's my sum of the forces. The sum of the forces is equal to the mass times the acceleration. I don't know what that acceleration is, but there's a good chance I'm going to be solving for it because that's what it asks me to solve for. I'm going to then write, using this equation right here, I'm just going to solve it for the force of the tension. So I'm going to add the mass of B multiplied by gravity to both sides, and I might factor one. Actually, I'll just write it like that. Mass of B multiplied by gravity plus mass of B multiplied by the acceleration. So now I have one equation to work with. I'm looking for the acceleration. Now let me look at Newton's second law for block number A, and I'll start by looking in the y direction. I write Newton's second law. Sum of the forces in the y direction for block number A is going to be the mass of A multiplied by the acceleration of A in the y direction. And in the y direction, A does not accelerate. So now we can kind of see that choosing our coordinate system as we did has paid off, because we can set A is equal to 0. And then we say upwards we have this normal force right here, force of normal. In the downwards direction, all we have is the weight minus the force of the weight. So 0 is equal to the normal force minus mass of A multiplied by gravity multiplied by cosine theta. Just use that guy right there. And solve this guy now for the normal force, simply adding mass times gravity times cosine of the theta to both sides. I can say the normal force must be equal to mass times gravity times the cosine of the theta. So now let me write the sum of the forces in the x direction for box number A, or box A. That's going to be equal to the mass of A multiplied by the acceleration of A. And again, the acceleration of A must be equal to the acceleration of B. These two guys are tied together, so I'm leaving off the subscript right there. And let me just highlight really quickly the forces in the x direction. It's getting a little bit complicated here. I've got the tension in the negative x direction, the friction in the positive x direction, and then the weight in the positive x direction here. So force of friction plus the weight, the mass times acceleration times g sine of theta in the x direction right here. Subtract the tensional force, and I have Newton's second law for box A in the x direction. And now what I can do is I can say, well, I can take my tensional force that I solved for right up here, and I can plug that guy in right there. I can take my normal force, and I know that the force of friction must be equal to mu sub k times the normal force. Use that relationship and use the normal force, add those two guys together, and I can plug those in right there. So I'm going to do that. First I'm going to write the mass of A multiplied by the acceleration. Now that's going to be equal to the frictional force, which is mu sub k times the normal force. So mu sub k. Now my normal force I use from this guy right here, and that's going to be mass of A multiplied by gravity times cosine of the angle, plus that guy is unchanged, multiply gravity times sine of the angle, minus the tensional force, which again I get from right up here, mass of B multiplied by gravity plus mass of B times the acceleration. And now you can see all I really need to do is subtract mass of B from both sides, and I can get an equation describing, or there we go. I can add mass of B multiplied by A. I need to take this minus sign right here and work it through. I can add the mass of B to both sides and end up with mass of A times the acceleration plus mass of B multiplied by the acceleration. What I did on the last step was I want to isolate my acceleration on one side, and over on this side I'm going to have all of my leftover terms. my normal force. And then that minus sign goes right there as well. Now I can pull out the like term, the acceleration. That's going to be equal to all that stuff. And I divide both sides by mass of A plus mass of B, and I'm going to end up with all of this stuff divided by mass of A plus mass of B. Now, all of the setup, all of the physics was simply using the free body diagram. This stuff right here, that's all just algebra. Now, I know what mu sub k, mass of A, g, cosine theta, I know what all of these guys are. I know that theta is equal to 34. So I'm not going to explicitly write that out. This would make that even more confusing. But you plug all those guys in. I highly suggest you do this. Actually, do this. And you end up with 1.6 meters per second squared. So that is the acceleration of the system. Now it asks you, what is the smallest value of mu sub k that will keep the system from accelerating. Now that is actually something that we can work with simply by backing up by 2 steps and saying, here we have an expression for the acceleration of the system in terms of all these other parameters, and it's asking me for what value of mu sub k will make my acceleration equal to 0. So now I say 0 must be equal to mu sub k, all this stuff right there, and now I simply just have to go ahead and solve for mu sub k. I know what all those angles are, I know what all those masses are, and at the end of the day I'm going to come up with mu sub k is equal to 0.53.